So, I remind you that we discovered that for solids, the oscillations are not of independent particles, but of independent quasi-particles, basically standing waves inside the materials. We call them phonons. They are described by simple harmonic oscillators, in a sense, but they are not real particles, quasi-particles. Standing waves, and still we need somehow to count them, right? Because we don't really know what are the different omegas. Okay? If you're thinking that each of the particles, each of the phonons have EI, this is energy of phonon with frequency omega, or just specific omega, EI, according to Einstein, is going to be n h bar omega. N is an integer, omega is some number, and we know that we have 3n in total, 3n particles, or phonons in total. Okay, so this is what we have, and we have no idea what are those different omega i's are. Now, the idea of dpi is to say, well, if I know that those are standing waves, not dying oscillations, I can count them. How can I count them? Because there are specific restrictions on the number of standing waves that can be inside any material. Why? Due to the boundary conditions. The moment that I have boundary conditions and I know that some specific standing waves have to survive inside the material, there are some constraints that I can use. Now, so if I'm using, let's say I'm starting with one-dimensional system, and this one-dimensional system is string of length L. Now, inside the string there is a lot of particles, there are some specific waves, and I know that if I have k is my wave vector, well, if in 1D it's going to be wave scalar, it equals to 2 pi divided by lambda. What is lambda? Is the wavelength. Wavelength. And k is the wave vector. Now, I know that L divided by lambda divided by 2 equals to n integer. An integer number of half of the length waves have to be settled somehow inside my material of length L. So here I have a connection, okay, between k, L, and n, right? Because I can write down lambda as 2 pi divided by k. So L divided by 2 pi divided by k divided by 2, okay, equals to n. So in total, I obtain that L divided by pi multiplied by k equals to n. Okay. I have a connection between specific k and specific n. Now, this is for specific n. I want to ask how many wavelengths or how many different waves can survive or can be settled in a material up to a specific number, specific wave vector. Okay. I basically have to count all the different n's that contribute to different states or to different standing waves up to a specific k. Okay? So let's assume I'm saying the following. How many n's are there such that all the n's are less than a specific n max. Okay. So basically I have a restriction, n less than some n max. What is this n max? N max is related to my wave vector. L divided by pi multiplied by k. So how many wave n's are there? There are 1, 2, 3, 4, 5, up to n max. So the total number of different states up to a given wave vector is just L divided by pi multiplied by k vector. Okay? So L divided by pi multiplied by k, the total number of states. Okay. I will repeat myself. I want to count all the possible waves, standing waves, that can be inside my system up to a specific wave vector. Why? Because I actually want to see what is the density of the states for a specific k. Okay, so the problem is, I'm going a little bit backwards, are with those wi's, omega's. I don't know anything about them. They don't have to be integers. I don't really know what they are. The only thing that I know is that, well, if I do not know nothing about them, maybe I know something about their density. Okay? And the way to find the density is to say, well, let's count all the states that can be inside the system up to a specific omega, and then take a derivative of this number with respect to omega. Okay? So the density is d to d omega number of states. Okay. And number of states, okay, I just count them. What is the number of states? Is the number of different standing waves that survive in the system or can be in the system up to a specific n max. This n max is related to my wave vector. Okay, so basically density is d to d omega of L divided by pi multiplied by k. L is not related to omega, pi is not related to omega, and I obtain that this is L divided by pi dk omega d omega. Now, why I write down dk to d omega? Because for any material, there have to be a dispersion relation. The wave vector is somehow, or the magnitude of the wave vector is somehow related to the frequency, to the omega. Something. A dispersion relation. So you see the way how Debye looked on it, he said, well, if I know the dispersion relation for a given material, okay, let's think that I have a knowledge about how the magnitude of the wave vectors inside a given material are related to the frequency of the oscillations. Okay, so if I know this k of omega, I can go backwards, at least for one-dimensional system, and I can say, well, the only thing that I need to do is to count the number of states. And the number of states, well, it's easy to count because I just need to know all those integers which arrived where they arrived from the condition that those are only the standing waves inside the system. My states are the standing waves inside the system, and I can count their number. And the moment that I know their number, I can obtain the density of the different omegas. So it's density of different omegas. Okay? So this is the idea of divide. It says you assume something about the dispersion relation. The moment that you know the dispersion relation, you find the total number of states using a specific wave vector or magnitude of wave vector. The moment that you know it, you take a derivative with respect to omega and you have the density. That's it. Okay. So we have done this for one-dimensional material. Our original problem, it's not one-dimensional, it's three-dimensional, right? So let's assume that our material is a box of dimensions L by L by L. Okay? So L to the third is the volume of our material. Now I repeat myself, okay, with this idea. Let's count the number of standing waves not inside in one-dimensional material, but inside of three-dimensional material. Now, for three-dimensional material, I'm looking on this guy. I'm saying, oh, this is actually only for one dimension. Let's rewrite our argument again. So lambda equals to 2 pi divided by k. Lx, for example, divided by 2 pi k x divided by 2 equals to nx. And Ly divided by 2 pi divided by ky divided by 2 equals to ny. And Lz divided by 2 pi divided by kz divided by 2 equals to nz. So instead of one integer, we have three different integers, an x, an y, and an z. Or I can say the following thing. Out of those three equations, let's write down the vector form of kx, ky, and kz. Right? I can write down this in the following way. So from here, I obtain that kx equals to nx divided by L multiplied by pi. So I'm assuming that Lx, Ly, and Lz, they all equal to each other. It's easier. From here I obtain that ky equals to pi divided by L multiplied by ny. And from here I obtain that kz equals to pi divided by L multiplied by nz. And in total, I'm writing down my k vector as pi divided by L multiplied by nx, ny, and nz. And in order not to drag this L, but because I want a relation to the volume, I write down, instead of L over here, I write down K as pi divided the volume to the third, 1/3, and X, and Y, and NZ. Now, the next step, for one-dimensional system, it was, let's calculate all the number of states that can survive up to a specific magnitude of my wave vector. Okay? Count all the states that all the states in the system for nx, ny, and nz smaller than the k vector. Okay. Now, because I want to operate, so the question is why it's important to enter inside volume and not just length, because I want to operate with a general volume of the system. That's it. Okay, next step is as follows. So what we have done in one-dimensional system. So in one-dimensional system, we had only one integer, which is nx, for example, and we count all the different number of states up to a specific n max. And this n max was just k multiplied by L divided by pi. Okay? This is what we have done in one-dimensional system. In three-dimensional system, it is different, right? In three-dimensional system, we can have different variations of nx and ny's and nz's. So we are not looking on the states or just the integer numbers that are sitting on one-dimensional y. We plot three dimensions. And in those three dimensions, we have nx, and we have ny, and we have nz. And there are many states with different ny's and nx's and nz and z's. Okay? And they fill up three-dimensional space. So there is some sort of a three-dimensional lattice over here. And I'm asking the following question. I want to compute the total number of states such that the vector, or all those states, are smaller in magnitude. Their vector, the vector to them, is smaller in magnitude from this k. Okay. So count all the states such that the distance of these states to 0, 0, 0 is smaller than my vector over here. So it is k v to the 1/3 divided by pi. Right? Because if this is the k vector, up to this point, I need to find out what are the different states. The radius of this vector it is square root of nx squared plus ny squared plus nz squared. Right? There is some specific radius. And I know that this radius is equals to the size. So instead of this guy, nx squared plus ny squared and z squared equals to k divided by pi multiplied by v to the 1/3. So this is the magnitude of my vector multiplied by v to the 1/3 divided by pi. And I need to count all the different states, okay, that are sitting in a specific portion of my space such that they are part of, well, it's a three-dimensional ball, I can say, but they are sitting inside this ball, and there are restrictions is that nx has to be positive, ny has to be positive, and then z has to be positive. So I have to calculate the volume of this ball in 3 dimensions and only take one specific part of it, okay? Because I don't care about those numbers when ny's are negative or nz's are negative or ny's are negative.
But
yes.
you also don't care about when nx is equal 1/2 and you are counting it.
Okay, okay, oh, great, great. So you're saying the following. If I'll take the volume, okay, if I'll take the volume, this is going to be the volume of the space. Now, how do I count the different numbers inside a space? Now, if I assume that each state it's not a point, but it's actually occupying a 1 by 1 small cube inside this space, right? So basically, I'm saying what I need to count is the total number of cubes that are sitting inside my 3-dimensional space. And that's it. Okay? So you're right, I'm counting points. But the way to count points is to count the volume and say each point contributes a specific small volume of order 1. That's it. So, if this is my vector, what is the volume of a 3-dimensional ball that has this vector over here? Do you remember the formula? The number of states. It's just the volume. So it's volume in space, in states space. And it is equals to 4/3 pi radius to the what power? 3. This is what we need? Why divide by 4? Not 4? 8, right? Because we are taking, so there are 8 quadrangles over here, right? And x and y and z is positive, so we are talking only one of them. So it's multiplied by 1/8. 1/8. Okay. So the number of states equals to 1/6 pi multiplied by the radius, which is k v to 1/3 divided by pi to the 3rd power. Okay, so this is the number of states.
Can I ask another question?
Yes, sure.
When you are saying that each point occupies a cube with a specific volume,
think about in 1 dimension. So in 1 dimension, I want to, so this is 0, this is n max. Let's say this is 3. So I have 1, and I have 2, and I have 3. So what I'm saying, instead of counting points, which is easy in 3 dimensions, so I have, oh, here I have 3 points, very, very easy. I'm saying, let's count the length. This length equals 3. How many points are? I'm saying each point is associated with the unit length of 1. Okay? So the total length equals also to the total number of points. The same thing I'm doing in 2 dimensions. Let's assume that I have several points over here. Okay? So what I'm doing, I'm counting area, and I'm saying that each point is associated with a specific small area, okay, with a specific small area, and the total area is going to be just the number of points that I have inside my system.
This is a very specific case because you have a cube in your total system. If you have like a cylinder in your total system, the density of the ends wouldn't be a constant. You will have to use some Bessel function and go and get.
So you're saying the following. You're saying the following thing. So you chose a very simple figure, which is a ball, which is a circle, which is a line in your examples. Yes. If your configurational space, if you're the space that nx and ny and z is going to be something more complicated, yes, it's going to be more complicated, but where the complication is going to come from? It's going to come from calculating your total volume. And that's it. So for simple figures, the total volume is something simple. If I'm going to have some very crazy material, okay, yes, the calculation of the volume is going to be something more difficult. Don't worry, I won't ask you to calculate crazy functions. Okay. Right? So usually a line, a circle, a ball is more than enough. So this is the number of states. Now let's calculate the density of states. Density of states is you take the total number of states and you take a derivative of this number of states with respect to omega. Okay, so density, let's call it d of omega, density of states, equals to d to d omega, because then I only care how many states there are at specific omega. So the way to count it, to measure it, is to count everything and take a derivative. So d to omega, d to d omega, the total number of states equals to d to d omega of what we have inside. It's 1/6 pi k to the third volume to the 1 divided by pi to the third. So let's erase pi and make pi square over here. And it equals to 3 divided by 6 v pi squared multiplied by dk or k squared of omega dk to d omega. So we can replace this 3/6 by 1/2. This is our density of states. And second, we will understand. So I just know the following thing. It's like in mechanics. In mechanics, we start with discrete masses, right? And when we deal with discrete masses, we just need to count all the different masses. Okay? So if we had discrete particles, we need to count all the different discrete particles. But our omegas are not discrete. So like in classical mechanics, when we go from discrete mass to continuous mass, we need to introduce something which is called mass density. Here, we're going from discrete specific particles with discrete omegas, we are going to continuum representation of our spectrum. Therefore, we cannot count all the different particles. We say we will integrate, and we will integrate over the density of omegas. Okay.
אפשר שאלה?
Yes.
מספר המצבים אבל שקיבלנו הוא לא מספר שלם.
Well, approximately it's something.
זה לא יהיה בעיה?
In what respect? Problem according to what?
כאילו זה קירוב מספיק טוב?
Okay, so I will answer this question. So there is a number of states that I somehow counted, okay, which is a specific number. The only thing that I care about is not this number, and whether it's an integer or not. The only thing that I care about is how this number is modified with omega. I only care about the derivative. So even if there are some additions of 1/2 or whatever, it won't be a problem because I'm interested in the density and not in the number itself. Right?
Okay. Yeah.
Any other questions? Okay, so let's make the following transition. So we know almost everything, but just we don't know what is k squared of omega and what is dk to the omega. Why we don't know this? Well, because nobody has told us what is the dispersion relation. What is the dispersion relation? Now, in general, the dispersion relation is something very, very complex. Okay, so you have to measure it. You can use some elastic approximations in order to calculate it, but this dispersion relation is something complex and it depends on many properties of the material. Okay. So if I'll plot, so this is my omega, this is k of omega. In general, it's something, and this something can be very, very, very complicated. Okay. So great, we calculated the density, we have a prefactors, we have a volume, we have pi squared, but the crucial part is this dispersion relation that relates the wave vector to the different omegas that are sitting inside the system. Okay. Now, Debye said the following thing. Said, well, yeah, I know it's very complicated, but let's make some assumptions. We model the system, we model our world. So what we are doing, Debye assumed the following thing. He said, well, let's forget about everything. I know that when omega is small, k omega is usually proportional to the omega. Though this is the part of the linear response or elastic theory. Okay, for small omegas, I can always say that the function is linear. Okay? I can always do that. Because when omega is 0, k omega is also 0 for elastic waves inside the material, and this is what we look on, elastic waves. Okay? Phonons. But let's continue this linear approximation forward. Let's say, well, all we have is just linear spectrum. Now, this of course cannot continue on and on and on and on and on, right? So Debye said, well, I have a linear spectrum and then I have nothing. Okay. So this is my dispersion relation. K of omega is a linear function of omega up to some specific value. Omega d, omega d. Omega Debye. It's symmetric, of course. And it goes linearly, and then it just drops to 0 and that's it. Is it true? No, it's not. In some sense, when omega are not extremely large, is it sufficient? Well, actually, yes. If we're not talking about huge fluctuations, but not so large vibration of our medium, this approximation is pretty good. Okay. Great. So, what is then this k square omega? So remember, we are talking about elastic waves inside the system, right? The particles are somehow fluctuating. We are talking about those oscillations, our standing waves, our phonons. Now, from the class on waves and elastic theory, you know that there are two types of modulations. Transversal, right? And longitudinal. Okay. So for a wave vector, I'm going to have the following thing. So k omega is going to be, for the transversal waves, is some specific ct multiplied by omega. Okay? And there is only one type of such waves. Why? Because if I have a polarization of the waves and wave is propagating in this direction, I only have one type of waves that can oscillate in the, well, this is CL then, in the longitudinal direction. Okay? Because the wave vector is in that direction, this is the propagation of the wave, so the oscillations can be only in this specific direction. There is only one type of such waves.
Stas,
Yes?
shouldn't it be 1 divided by C?
Omega
Equal to CK?
C, yes. Yes. CL.
No. No,
Yes.
this is still wrong.
It's still wrong, right? It's wrong.
You just moved it to the other side using
Yeah.
the algebra rules, but it was initially wrong. Okay,
Thank you.
yes, this is good.
I remember that I had to multiply something, but
Yeah.
what about CT? Thanks. How many relations I have of for the transversal waves? I have two, right? Because if this is the direction of the wave, the oscillations that are not longitudinal, they can be in this direction or they can be in this direction. Okay. So in total, I have contributions from 3 polarizations of the waves. Okay. So for a given k, I have waves that are oscillating like this. I have waves that are oscillating like that, and I have waves that are oscillating like this. Okay. And usually, the velocity is different from for the longitudinal waves and the transversal waves. Okay? So when I'm talking about the density, I have to talk about the density of longitudinal waves, I have to talk about the density of transversal waves of this type, and I have to talk about the density of the waves of this type. Okay? Now, for each of them, so let's call it dl of omega equals to 1/2 v divided by pi squared. Here I'm going to have k of omega squared, which is omega divided by cl squared, multiplied by the derivative dk to d omega multiplied by 1 over CL. I have d transversal, let's call it 1. It is 1/2 v divided by pi squared, omega divided by c transversal squared, multiplied by 1 over c transversal. And I have the third type, which is the second type of the transversal waves, cd2 omega. It is 1/2 v divided by pi squared, omega divided by ct squared, 1 over ct. The total density of states is the density of those waves plus the density of those waves plus the density of these waves. d omega equals to dl omega plus dt1 omega plus dt2 omega, which equals to v divided by 2 pi squared omega squared, and inside I have 1 over CL to the third plus 1 over CT to the third. So let's call whatever here in the parentheses three multiplied by 1 over C tilde to the third. Okay. Let's forget. I just in order I don't want to have CL to the third and CT to the third, etc., as if I'm considering that CL and CT is exactly the same thing. Okay? I'm just saying, well, everything here is just 3 multiplied by 1 over some velocity to the third. That's it. Basically, I'm saying let's consider the case where all the velocities, propagation, longitudinal, transversal, doesn't really matter. Okay, so in total I have 3 halves v divided by pi squared omega squared divided by c tilde to the third. No. So when you're talking about the different waves that I told you that are in x and in y and in z's were for each polarization of the vector. So it's rooted in the solution of the wave equation. The solution to the wave equation, you have 3 different functions. Okay, one that describes these oscillations, one that describes these oscillations, and one that describes this oscillation. And for each of them, you have to find the density. No. So if I have electromagnetic waves, then I have only transversal oscillations. But for elastic waves, it's not true. Okay? Because the material, take a particle. Okay? The particle can oscillate like this, like that, and like that. Now, for electromagnetic waves, it's not true. Why? Because you usually take a particle, an electron, and you oscillate it like this. And this is why you have propagation of wave over there, and oscillations are always transversal to it. So there is a very big difference between elastic waves and electromagnetic waves. Okay, so finally, what we have our density of states. We worked very, very hard to obtain it, and I tried my best to explain it properly, where all the different constants here arrive from. Now we are ready. What we are ready to do? We are ready to solve the whole Debye problem. Okay? So let's first write down what we have for Debye problem. In a medium, in a material, there are 3n phonons. Okay. Each phonon has an energy omega I and has energy Ni h bar omega I, and that's it. The density of omegas is provided by the omega equals to 3 halves v pi squared omega squared divided by c tilde squared, c tilde to the third. What we want to calculate the specific heat, CV. Right? Because maybe you have forgotten already, but the main question was the behavior of the specific heat for high temperatures and for the low temperatures. Right? Those are all the approximations that we made on the way. First of all, we recognize that there are independence, so we can use factorization. Independence, it's not of particles but of phonons. Each phonon have a specific energy. Omegas, we had no idea what omegas are, but Debye somehow managed to show us that we know the density of all the different omegas. Great. So now we can start our problem. So first of all, what exactly we can calculate right now. So let's look on the different statements that we have inside. What is the meaning of this statement that we have 3n phonons? Okay. And this is related to this question that I was asked, is the number of states of this n x and y and z when I calculated it, is it an integer, maybe it's not an integer, etc., etc. How I fix it? If it's not an integer, if it's something which is not an integer, how do I fix this? Well, I use this criteria. Why? Because I know the following thing, that when I will integrate on all the possible omegas that I have inside, so I start from 0 and go up to infinity, d omega, I should get the total number of omegas that there are inside the system. And what is the total number of omegas that I have inside my system? It's just the 3n. So each phonon contributes its own omega. When I count of all the possible omegas, I will count all the possible phonons. And this guy has to be equal to 3n. Okay? So even if I haven't calculated something correctly, maybe I miscalculated something on the way, I have this constraint. Okay, this is a very harsh constraint, right? So how we overcome it? So Debye, remember, what was the approximation of Debye? Debye said I have a linear approximation. This is why I introduced all those linear relations, dispersion relation, inside my density of state. But he also said, well, omega is not going to infinity. Omega going up to omega Debye. So I have instead of infinity over here, omega Debye. And this omega Debye fixes everything, right? Because even I have miscalculated something, it's just going to modify this omega Debye a little bit, right? So let's find out what is this omega Debye and how it's related to the other constants that we have inside the system, specifically the 3n. So what we know, that 3n equals to an integral from 0 to omega Debye. What is this d omega? This guy over here, which is 3/2 v pi squared omega squared c tilde to the third d omega. So you see from this description that I cannot simply say, well, it's up to infinity. Why? Because omega squared over here will cause the integral to explode. This is why I have to introduce this cutoff, not me, but Debye. Okay. So let's solve it. Let's take everything which is not related to omega outside of the integral. So we have 3/2 v pi squared 1 over c tilde to the third. Integral from omega 0 to omega Debye, omega squared d omega. You're getting 3/2 v pi squared 1 over c tilde to the third multiplied by 1/3 omega Debye to the third power. This is the right hand side. Left hand side is simply 3n. And from this equation, we're getting the omega Debye. So omega Debye equals to 2/3 n c tilde to the third multiplied by pi squared. No, it's just 6 pi squared divided by the volume. One-third. This is our omega Debye. Right? So even if we have calculated something, we have those small points when we calculated in the structural space the number of nx's and ny's and nz's, okay? And if we haven't got the specific number, everything can be fixed out afterwards by the omega Debye. Why? Because the only thing that I care about is that the total number of states should be an integer and a fixed number which equals to 3n. So this is my omega Debye.
אפשר לשאול שאלה?
Yes.
יכול להסביר עוד פעם אולי את השורה הראשונה, למה אינטגרל על ה...
Okay. So I have how many phonons I have? 3n, right? Now each phonon have its specific omega. So if when I count all the different omegas, okay, so the density of states, okay, is the amount of omegas in a specific material, a specific length, divided by this length, right? This is the density. So when I count of all the different omegas and I calculate this integral, this integral gives me the total number of all the different omegas that I have inside my system. So if you have, for example, a density of mass, okay, in a given material. Okay, so rho of m is the density of mass. And I'm asking you the following question. What is the integral over the density of mass in a string that goes from 0 to L, rho of L, dl? This is the total mass inside this material. Okay? The amount of all the different small masses. Okay? The same goes over here. This integral on the right hand side tells me what is the amount of all the total omegas that I have inside my system. And the number of all the omegas is just the number of the phonons, because each phonon gives me one specific omega. Therefore, this equality. Okay?
סטאס, למה במקרה הזה בחרת להתחיל מאפס, כאילו, ונגיד בציור והיה חשוב לך לצייר...
Because it's symmetric. Usually this is how the dispersion relation goes. But the only thing that matters to me is what I introduced in my density of states is the value of k. Positive value of k. Because it was the magnitude of the vector. Remember? This is why I only chose to integrate over one specific direction. Any other questions?
What is the physical meaning of omega de pi? It's just a mathematical constraint, but
Yes.
it has to have some physical...
It is the limit where the theory works. Okay, so this is our approximation. If you have a material, and this is omega d pi, and this is omega d pi. If you have a material that the linear dispersion relation breaks much faster before the omega gets to omega d pi, if you have something that looks like this, okay, the approximation won't work.
Okay.
So it's the limitation for the material or the elastic properties of the material where my approximation works. Okay, that's it. Okay, so we have now omega d pi, explained omega d pi. Let's try and understand how we calculate CV. Okay. So if I take one specific particle, in order to calculate everything, it's not a particle anymore, it's a phonon, okay? I need to calculate the partition function. The moment I know the partition function, I can calculate the energy, which is just a derivative with respect to beta of my Zi. Okay? And the moment that I know the energy, I can calculate CV by taking the derivative of my energy with respect to temperature. Okay? So if I had one simple particle, I will calculate the partition function. Then I will take the derivative with respect to beta. Then I will take the derivative with respect to temperature, and I will get my specific heat. The problem is that I have a lot of different omegas, right? So what we have done so far, well, we calculated the moment that we have factorization, the moment that we have independence, we do it for each and single particle, and then we sum everything up, okay? So basically, if we have independence, we then say the following. Okay, this works for all the particles together. Z is going to be multiplication I from 1 to 3n over Zi because I have 3n independent particles, which I'll call phonons. Now, what will happen? U is going to be minus d to d beta. This is log of Z, I'm sorry. Log of Zi. Of log of Z. Right? Now, what is log of Z? It's just a multiplication. So because logarithm that is applied to a multiplicative function, it just turns out to a summation. So we'll have minus d to d beta, a summation of a log of Zi. I goes from 1 to 3n. And Cv is going to be the derivative of u with respect to t. And that's it. The only problem is then how we calculate all the different Zi's. Well, it's easy, right? Why it's easy? Because let's assume that the omega of this specific Zi is just omega I. So Zi equals to a sum n goes from 0 to infinity e to the power minus beta n multiplied by h omega I. Okay. Now we already know what this sum equals to because it's a geometric sum. So it equals to 1 over 1 minus e to the power minus beta h bar omega I. Okay, so we know what is Zi. Great. The next step is just to take this multiplication, right? So Z equals a multiplication. I goes from 1 to 3n over Zi equals to a multiplication. I goes from 1 to 3n over 1 minus e to the power minus beta h bar omega I. And here we hit the wall because we have no idea, and this is why we calculated all those density of states and etc, etc, etc. We have no idea what is those, all the different omega i's. This is why we started with everything, right? We don't know what those omega i's are, okay? It doesn't matter if we don't know them for Z or we don't know them for U, right? I can write down the U. It'd still be the same. U equals to minus d to d beta, a sum. I goes from 1 to 3n of a log of Zi. So it's a log of 1 over 1 minus e to the power minus beta h bar omega I. Okay? The problem still stands. Omegas are unknown. This was the original problem. The solution of Debye says the following: great, you don't know them, but you know the density. If you know the density, so the only thing that counts is you need to count over all the different values of all the different omegas. Right? It's nothing there, nothing here, except the omegas. So when I need to calculate the sum, I just need to sum over all the different values omegas i's over here. Now, if I'm assuming that I don't have discrete omegas, but as Debye told me I have omegas that are, discrete, that are continuous, I'm saying, well, let's take this integral. The sum I goes from 1 to 3n, okay? Of a log of 1 over 1 minus e to the power minus beta h bar omega I. And we say, well, if omegas are continuous, it's not a sum, it's an integral. Integral of what? Well, this function. Log of 1 minus e to the power minus beta h bar omega. Omega now is a continuous variable. Now, for each omega, how many omegas are there? I need to multiply it by the density. D of omega is d omega. What are the limits of my integral? Well, they came from the counting of all the different states. So it's from 0 to omega d pi. And this is the solution. Okay? So instead of trying and solve everything in terms of let's diagonalize the matrix, etc., the moment that we identify that everything is independent, I use the regular structure of statistical physics based on factorization and independence. I arrive to some sum where there are, which is depends on only on the different values of the omegas that are inside the system, and then I switch and say, well, forget about discrete omegas. I do not know how to solve them. I have in my mind the elastic approximations. I will use those elastic approximations in order to derive the density. The moment that I know the density, that's it. I know everything. Okay? So from now on, if beforehand we had a lot of physics, a lot of approximations, this was the modeling part. We assumed something, we pushed it inside the model, we took something out, etc., 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 etc. Now we have a formula. Okay? Because we know that U equals to minus d to d beta of whatever stands inside. So it's just an integral now. That's it. Okay? Integrals are usually easy. So let's try and see what we have inside this guy. Now moreover, since the integral is over omega and the derivative is with respect to beta, we can take this derivative inside our integral.
Omega d pi does not depend on beta?
No?
Okay.
Right? So how it will depend on beta? We obtain omega d pi from elastic theory. Elastic theory couldn't care less about the temperature of the system. Okay. So what we have is just minus 0 omega d pi d to d beta log of 1 over 1 minus e to the power minus beta h bar omega. And here I have the omega, which was, please remind me, 3v 2 pi squared omega squared by cl to the third, something like that, right? Seems correct. And here I have the omega. Independent of beta, the only thing that depends on beta is just this logarithm over here. Okay. Next step is, well, what is this derivative over here? So it is minus. Let's take everything that is independent of omega outside of this integral. So we have minus 3v 2 pi squared c tilde to the third, an integral from 0 of omega d pi omega squared, and here I have 1 over d to d beta. No, I am taking the derivative of the logarithm. So it's 1 over 1 minus e to the power minus beta h bar omega multiplied by what? Multiplied by minus e to the power minus beta h bar omega multiplied by minus h bar omega. D omega. Okay. So basically what I have done, I said log of 1, I need to take the derivative of log of 1 minus e to the power minus beta h bar omega. So I said it is minus of d to d beta of log of 1 minus e to the power minus beta h bar omega, and it equals to minus 1 over 1 minus e to the power minus beta h bar omega, and then I had an inner derivative with this minus beta h bar omega multiplied by minus h bar omega. And remember that I also have an additional minus over here. Therefore, in total, I don't have a minus over there. Okay. So let's figure out what we have. So minus and minus cancels out. I have e to the power minus beta over omega. So in front of the integral, we have 3v squared divided by 2 pi squared c cubed to the third. Inside 0 omega d pi. I have, well, let's take h bar outside of the integral. We have omega to the third. Omega to the third, e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega d omega.
Why is v squared?
Omega squared?
No, v.
V squared, it's not squared. Thank you. Not squared. Okay, so this is u. I can write down, it's a little bit simpler in saying this 3v h bar 2 pi squared c tilde to the third, an integral from 0 to omega d pi, and here I have omega to the third divided by e to the power beta h bar omega minus 1 d omega. So this is u. Okay, nice integral. Now, the last part is, well, we are interested in the specific heat, which is du to dt. Okay. Another derivative of whatever we have with d to dt, whatever we have over here, 3v h bar 2 pi squared c tilde to the third, an integral from 0 to omega d pi of omega to the third power e beta h bar omega minus 1 d omega. Now again, the same trick. Omega d pi is independent of the temperature. All of this is independent of the temperature. Omega is independent of the temperature.
Why is the speed of sound independent of the temperature?
We assume that it's independent of the temperature.
Okay.
Those are the elastic properties. Okay, so the elastic properties are independent of the temperature. Great. Next thing is as follows. Let's take this derivative inside the integral. So we have 3v, and you could ask the same thing before, right? But you've somehow been quiet over there.
I missed it.
Okay. But it's the same thing. I assume that everything, the speed of all the elastic properties are independent of the temperature. This is an assumption. It will break down at some point. Yes. 3v h squared h bar 2 pi squared c tilde to the third, an integral from 0 to omega d pi, omega to the third, d to dt, 1 over e to the beta h bar omega minus 1 d omega. Okay. So we have to take the derivative of d to dt of 1 over e to the power beta h bar omega minus 1. It equals to minus 1 over e to the power beta h bar omega minus 1 to the second power multiplied by the inner derivative. The inner derivative is e to the power beta h bar omega multiplied by h bar omega d beta to dt. Okay. Now, what is d beta to dt?
Negative 1 over k times t squared.
Let's write it down. So d beta to dt is d to dt of 1 over k Boltzmann t equals to minus 1 over k Boltzmann t squared. Okay. We're almost there. We're almost there. So CV equals to, we have a lot of junk here. 3v h bar 2 pi squared c tilde to the third. Now we have inside the integral 0 omega d by. We have omega to the third. We have omega and we have h bar. Okay. So we have h bar, omega to the third. We are going still to have e to the power beta h bar omega. E to the beta h bar omega. We still have e to the power beta h bar omega minus 1 to the second power. We had this minus and we have that minus. Okay, so the minuses cancels out. So we have 1 over k Boltzmann t squared d omega.
So omega
F4. So we started omega to the third, so it's omega to the fourth. Omega to the fourth. Okay. Omega to the fourth. Right. Seems like I got it right. Okay. All right. So let's take everything out. So CV equals 3V h bar squared 2 pi squared c tilde to the third 1 over k Boltzmann t squared integral from 0 to omega d by omega to the third power e beta h bar omega divided by e to the power beta h bar omega minus 1 squared d omega. And I think that I got it right. Okay, very nice. All right, so this is CV. It's kind of an ugly function, right? So it's an integral. Well, everything here looks okay. Whatever here is not exactly clear. Right? So first of all, let's write down again what is omega d by for the completeness. So omega d by was, do you remember what was our omega d by? I just remember that it's 1/3 of something. What was inside this 1/3? 6 and c tilde to the third pi squared divided by v. Okay. So this over here is the complete expression for the heat capacity. Now let's try and see what happens. So it's obvious that I cannot really go from here to anything else because it's not that it's not a simple function. Okay, it's not that I can do something again, invent a crazy integral and say, oh, eventually it's a sine or a cosine or whatever. No, this is this function. It's the ugly function that stays over here, still stays over here. Now, what we have done for the Einstein relation, where the heat capacity, Einstein model, where the heat capacity was simpler, we took the limits. We took the limits of large temperatures and we took the limits of small temperatures. Okay. So what we are going to do now, we're going to take the limits t goes to infinity, and t goes to 0. Okay. Okay, so in order to do that, you see where temperature enters. Well, there is a prefactor that depends on the temperature, but that's rather simple, so I don't really need to do anything with whatever stands over here. But inside my integral, the temperature enters to the exponents. Okay, the temperature enters to the exponents, and when I'm taking the integral or performing the integral, I have a large parameter beta, or a small beta is going to be either large or either small, so it's large or small, depends, inside the integral. I don't really like it. Okay, so what I'm going to do, I'm going to try and take whatever the dependence of beta of all this function, I'll try to get it out. Okay, so I'm saying the following. Let's look on this integral. 0 to omega d by omega to the fourth e to the power beta h bar omega divided by e to the power beta h bar omega minus 1 to the second power d omega. Now, I want to say that let's call beta h bar omega, I call it u. Okay, I simply call it u. So when I use the substitution, so what I get is that d omega equals 1 over beta h bar du, or d omega equals to k Boltzmann t divided by h bar du. Okay. So this integral is an integral from 0, when omega equals 0, u equals 0, to omega d by, so when omega equals to omega d by, u equals to h bar omega d by divided by k Boltzmann t, h bar omega d by divided by k Boltzmann t. Okay, and here I have, instead of omega, I have u divided by h bar beta h bar to the fourth power. I have e to the power u. I have e to the power u minus 1. And I have k Boltzmann t divided by h bar du. Sorry? Oh, square. Yes. Okay, so my CV, before I take this limit, so this looks actually nice. Why? Look, I can take everything that is dependent on t outside of the integral, and the only dependence of this integral on t is going to be of the upper limit. Okay, so CV equals to 3v h bar squared divided by 2 pi squared c tilde to the third 1 over k Boltzmann t to the second power. I have k Boltzmann t divided by h bar, and I have here k Boltzmann t divided by h bar to the fourth power, an integral from 0 to h bar omega d by divided by k Boltzmann t, u to the fourth power, e to the u, e to the u minus 1 squared du. write it. So it's 3v 2 pi squared c tilde to the third. I have k Boltzmann, and I have k Boltzmann, and I have k Boltzmann to the fourth. So in total, I have k Boltzmann to the fourth. I have h bar squared. Was it h bar squared everywhere? H bar squared. No, it wasn't squared, right? So
No.
so where
It
it's
was correct.
בתוך האינטגרל יש לך עוד אחד.
okay. So h bar squared is right. So h bar squared, h bar to the third. So in total, I have h bar to the third. No. I have h bar to the fourth, h bar to the fifth. So h bar to the third. And I have t squared, t to the third, so t to the third.
No, above.
Above. Okay, and here I have 0 h bar omega d pi divided by k Boltzmann t, u to the fourth, e to the u, divided by e to the u minus 1 squared du. Okay, so now we have everything that we need, and the only thing that is left is to compute two limits. Well, we don't touch the prefactor, we only look on this integral. Okay, so the limit of large temperatures, what do I have? I have an integral from 0 to h bar omega d pi divided by k Boltzmann t of u to the fourth e to the u divided by e to the u minus 1 squared du. Let's take the t to the 0 limit first. Okay. We look on this integral and we say, well, when t goes to 0, whatever is inside the integral is independent of the temperature. Where is the only dependence on the temperature? It's in the upper limit of the integral, right? So when I take t to the 0, what happens to the upper limit of the integral?
Infinity.
It becomes to infinity. So all of this in the limit of t goes to 0 is simply an integral from 0 to infinity of u to the fourth e to the u divided by e to the u minus 1 to the second power du. Is it depends on the temperature somehow? Actually not, right? So what is this integral? Right? We can compute it. We can compute it by parts. Okay, so I'm going to say, let's call it a number. I don't have time to compute it, but it's a number a. This a is independent of the temperature, is independent of anything. Okay, it's some number. So what we obtain that Cv in the limit of small temperatures goes as this number a. Okay, multiplied by 3v divided by 2 pi squared c tilde to the third, k Boltzmann to the fourth, h bar to the third. Nice, very, very nice, but, and there is a but over here, it's t to the third. So do you remember why we started all of this mess? Huge, enormous mess. This huge, enormous mess was because the Einstein model failed in the limit of the low temperatures. In the limit of the low temperatures, the experimental observations told us the following thing. So this is Cv, this is T, divided by 3n. It went to a constant, 3 kb, and the convergence towards 0 was proportional to t to the third. Okay, so we work extremely hard. So this is the whole idea of divide. You cannot use the simple particles. You cannot assume that all the particles are independent. They're dependent. You cannot use all those simplifications by Einstein. You have to prove that there are phonons. You have to prove something about the distribution of the frequencies of the phonons. You have to work really, really, really hard. There is a prize at the end. The prize is that indeed you get everything right. Okay? Indeed, you can go into the experimental and say, yes, I got this t to the third, and I actually now understand what happens. Okay? What happens? What happens is that instead of single particles doing something like this, I have the whole system, have more phonons that are moving in cohort. A lot of particles doing something together. And when I use this assumption, I get the exact result. Okay? So I understand the physics now. I understand that small temperatures, no independence. Small temperatures, some sort of independence, but the only thing that matters is coordinated motion of a lot of particles together. Okay? So what the system prefers to do is not that there should be some single particle doing whatever it's doing, is that the whole system have to do something together. This gives the right result. Okay? So we got the right result and we understand the physics. What about the other limit? Okay? What happens when t goes to infinity? Okay? If you really want, I would calculate this number a. It's related to Riemann zeta function, and it's eventually 4 divided by 15 pi squared. It doesn't really matter, but it's a number. What about the other limit? Because, well, you know, Einstein was right over here, divide was right over there. Everybody writes somewhere, right? But the beauty of divide is that when we take this t to the infinity limit, we obtain the exact result as Einstein did. Okay? So what we need to do is to perform this integral from h bar omega d pi divided by k Boltzmann t, u to the fourth e to the u divided by e to the u minus 1 squared du, which goes to, now t here goes to infinity. So when t is large, so the lower limit is 0 and the upper limit is also 0, so you can say, well, yeah, so let's do this 0 from 0, right? And everything equals to 0. Which is a stupid approximation. Well, never do that, right? You cannot just simply assume here 0. Why? Because, well, everything then becomes 0, and it is completely wrong. So what do? Say, well, the integral is not 0, it's something. But I know that u belongs to the interval from 0 to h bar omega d pi divided by k Boltzmann t. Meaning, is u goes to 0 all the time. U is small. Okay? So when u is small, I can approximate all this e to the u minus 1, etc. by using the regular approximation. So when eu is small, so it's e to the u, I will approximate it as 1. And e to the u minus 1, I will approximate it as 1 plus u minus 1 equals to u. Okay? I'm going to use those approximations because, well, I can use here e to the u, it's 1 plus u, but I don't really need this. So when we substitute everything inside, what we have is that this integral from 0 to h bar omega d pi divided by k Boltzmann t, and here I have u to the 4 multiplied by 1 divided by u to the second power du. So we have an integral from 0 to h bar omega d pi divided by k Boltzmann t, u to the second power du. It equals to 1/3 of h bar omega d pi divided by k Boltzmann t to the third power. Okay. So CV was 3/2 V, whatever we had over here, multiplied by 1 over T. I'm sorry, T to the third power, multiplied, so T goes to infinity, multiplied by 1/3 H bar omega d, H bar to the third, omega d to the third, K Boltzmann to the third, T to the third. The nice thing is, it becomes independent of the temperature. T to the third over here, T to the third over there. So CV goes to a constant when T goes to infinity. And this is exactly the same constant when we substitute what exactly omega d pi is, etc., etc., etc. I don't have time for this, but when we substitute this constant, we will get exactly the 3k Boltzmann as we got for the Einstein model. The same constant as in the Einstein model. So the de Boy model, it's not only working in the low temperature regime, it also works in the high temperature regime. Right? So it fits all the different temperatures that we have inside us, we can actually reach. It converges to the T to the third, it converges to a constant, in between it's doing something, but those are the important limits, the universal limits, and now we understand them. Okay? So it's not just some independence of some particles. Phonons are crucial in order to describe properly the system. Independence of those phonons is crucial to describe the system, and moreover, eventually, everything is defined by the elastic modes of the system, right? So what we have pushed inside, the description of Debye, that there are some standing waves, and those standing waves have a specific representation by the density of states. The only thing that determines how solids are behaving, how they are heating up, how they are absorbing energy, is by the notion of those solids. So what Debye basically tells us is that not every particle starts to jiggle as something, but there are groups of particles that are starting to jiggle together, and they are jiggling in a very specific way of low temperatures such that the large group of particles are doing something together. This is why it gives us the T to the third power. At high temperatures, every man to himself. They don't care about each other anymore. There's a lot of small jiggling, but always the absorption of heat comes in a way of waves inside the system. Independent waves or cohort waves. Okay, so we finished Debye, and we will continue to the next example next week. Some final words about the quiz. The quiz won't include the Debye model. It will include the Einstein model. So everything that we have learned up to the Debye model is inside the material for the quiz. That's going to happen next Wednesday at 8:15 in the morning. You don't have to learn anything about Debye for the quiz. Good luck.
Thank you.
כן.
אולי יש איזה חוסר בהבנה, אבל אנחנו טוענים שכל החלקים זזים באותה תדירות, אבל...
לא. שיש לך קבוצות שלך, שיש לך גלים